All right, hi everybody, it's Elijah, and we're gonna get started here for our lecture 2, part 2, and hopefully everyone's doing okay. My voice is getting a little bit better, so I should be good to go again Monday. Sorry for the delays, just because I haven't been feeling well, and as you know, my voice has not been good. But I think we're according to schedule and timing with everything with these recorded lectures should be okay. If you remember, the first lecture let you guys out early, and I had a recording for that. And then for this, we're going to get a head start on chapter 4. And I'm going to make a recording, which you're going to watch now. And it's just going to go through some derivations and what the equations you're going to be using for homework. But we're not going to be doing any examples yet. I'm going to be doing those in class on Monday. So what I wanted to do is kind of just go through the derivations. And then once we get to class on Monday before your quiz, we're going to do some examples and actually get a better understanding. So if you happen to not watch this recording in time, you can always watch it later and understand the derivations later if you wish. But once we get the equations, that's what we're really going to be using for homework and exams and quizzes, right? So we're going to get started here. I don't think this will a lot of math, but I don't think it'll take too long. It's just stick with me here and we should get through this pretty quickly. Right. So lecture 2, part 2, chapter 4. And depending on your edition of the textbook, it kind of varies. But we're talking about Bernoulli's equation today, and chapter 4 is Bernoulli's equation. So agenda is, I'll get my pointer here. See, my voice is still recovering, but it's getting there. So chapter 4, we're going to learn how Newton's second law is for a streamline. And basically, we're also going to derive that into Bernoulli's equation. So I'm going to put that in there. So yeah, we're going to talk about Newton's second law for a streamline, which gets us to Bernoulli's equation. And we're also going to talk about confined flows and mass flow rate, just more equations here. Okay. And we're going to do a quick quiz reminder for Monday. Okay, so what we're going to talk about right away is streamlines, which is essentially used to describe flow in a fluid. So here, let's jump straight to the pictures. Right, so this picture A, you have an XZ plane, and this is kind of showcasing the streamline for a fluid particle. Right, so this is kind of 2 points, location 1 and location 2. And I'm going to kind of define everything there. V is going to be your velocity vector for the fluid there. And then here you have your graph B here. So same thing, you have your Z and X axis, right? And then I'm going to go over these variables here. So you have your particle as well. You have an S here, an R as a function of S, right? And then these N values. Okay, so we're going to go back up here. So streamlines are essentially lines tangent to a velocity vector throughout flow. So that's basically, if these are your velocity vectors, right, your lines are just tangent to this velocity vector. And so V is your velocity vector, which is a time rate of change of the position of the particle. S is the distance along the streamline. Right here is S shown. R is the radius of curvature, which is a function of S. And N is the coordinate normal to the streamline, which is this N value here. And they also use these N's to kind of number these streamlines. Okay. And the reason why I wanted to talk about streamlines is because we're going to apply a free body diagram to a fluid particle, which is along a streamline, which is this kind of orange-brown color you see here. And we're just going to be doing this with pressure and gravity. So FBD, if I abbreviate it, it's free body diagram. I'm going to try my best to kind of always put what abbreviations are so there's no confusion. Again, so this is just showing the derivation of how we're going to get to Bernoulli's equation. And it's a famous equation for fluid mechanics. That's like the one equation I remember. What you're also going to remember from this class is kind of an equation that gets you different pressures, different densities, and we're going to go over that later in a second. But this is just a derivation of how to get there. Okay, so let's look at this free body diagram here. There is a lot going on. but we're going to take this step by step, and then we're going to walk through the equations. So here, right here in blue is the particle. And to stick with me here, hopefully I can explain this fairly clearly. So let's always start with the axis, because that's kind of, the easier way to go about it. So this axis here is going in this direction is your n vector, and then they're unit vectors, right, which is just a magnitude in direction of 1, which is normal to your particle. And then you have your s vector here, which is along the streamline. Okay, and delta n is basically the change of your distance here, which is your n, and delta s is a change here in this distance in this s direction. Okay, so right, ignore everything. That's kind of, we just defined our axis and what these deltas are. And now what we're going to define is, let's talk about what this weight is, right? This is just your weight of the particle, and this is just showing its trigonometry. So this is the angle theta for this, right? This is your weight, or change in weight, delta weight. And this is change in weight because, these particles are changing in the fluid, right? Depending about the other fluids next to them. So here you have your weight in the normal direction, weight in the streamline direction, and right, this is the hypotenuse of that weight. And here, right, we already talked about this, your particle thickness. Sorry, we didn't talk about this. This is your delta y is your particle thickness. So that's another direction there. And here we're assuming that the shear stress or shear force is 0, right, which we made from previous assumptions from previous lectures. Okay, and then here are the pressures applied, right? So this P is essentially just a pressure that's applied to your fluid particle. And then these are the extra terms, I guess, to kind of make this force. So delta Pn, right? So that's your change in P in the n direction. And then it's multiplied by your change in s direction and change in y direction. Okay. So, right, if you do your dimensional analysis, you multiply these in here, right? That's just going to give you a force, right? So that's what that is. And then here, going up the n direction, you have your pressure minus your change in pressure in n times your change in s here and change in y. And then right, shear stress is still 0 here. And then here's this is the direction of the streamline, right, in the s direction. So you have your pressure plus your change in pressure in the s direction multiplied by the change in n times the change in y. And then your the other direction here, you have P minus delta P times your change in n direction times your change in y direction. And right, so your particle thickness is the y direction, so that's coming in and out of the page. Okay, and here's just showing you some trig, right? Delta S, delta Z, your theta along the streamline, right, which is here. And here is your normal to streamline, delta Z, delta N, and the theta here. So normal's in this direction. So I would, if you are trying to follow along with a derivation, if any of these are confusing, please rewind, right? Gravity is just pointing downwards. I probably should have explained this particle thickness delta y earlier, because you see it in many parts here of these forces. But delta y is just coming in and out of the page. Okay. Okay, so let's get started. We're going to derive the Bernoulli's equation. So we're applying Newton's second law to the particle. So it's F equals ma. This subscript s is just along the streamline, okay, which is this here. So before summing our forces, right, usually you sum your forces, right, and then you have your ma. Let's just define our ma now, which is your delta m multiplied by your acceleration in the s direction. Okay, so here your delta m is equal to rho times change in volume. So remember when I was kind of in our first lecture, this v with a cross in it, what is so scary about it? It's basically just your volume. So and I guess I just realized this now. It's just trying to differentiate your velocity v, right, which you're normally used to for v, and then volume v here, so you don't get these two variables confused. Okay, Delta V is also essentially your change in volume is your change in S, N, and Y direction, right? So that's N direction here, S direction here, and then Y direction in and out of the page. Okay, so now we have our, right, so delta M, then this becomes your velocity partial derivative of your velocity with respect to the S direction. And now you can substitute this in here, and this is your equation now. And now your left-hand side of the equation for your MA essentially ends up being this, which is your density, change of volume, velocity, and then partial derivative of velocity with respect to the S direction. Okay, so we're not summing anything yet. I just put this here just to have it. This is just your M equals A in terms of the terms that we've been using in class. Okay. Sorry. Okay. Sorry, that was being weird there on my keyboard. Okay, so now what we're going to do is sum the directions of forces, right, for the streamline. So here we're essentially just adding weight and net pressure force. Okay, so weight here, and sorry, I know I said S in the streamline, but this S is in the S direction, right? It also stands for just a streamline, which I already said earlier. So this weight here, okay, is essentially just your negative W here times the sine of theta, which you can see in the trig that we explained earlier, right? Sine opposite over hypotenuse. And this is equivalent if you do the units and the dimensional analysis of your specific weight times the change in volume, still in the sine theta direction. Okay, and now we're adding our net pressure force, which is the pressure forces, right, applied to this particle. So here we have your, we're going to try to map this out here. You have your P minus delta PS times your delta N delta Y, which looks like right here, right? And then you have your P plus delta PS times delta N delta Y, which is, that looks like right here, right? So this is getting subtracted from this because they're in opposite directions, you can see. Okay, you sum them up, right? Then you get this if you do the math. And here, if you look at the textbook, you have to kind of read it, but there is a substitution here for this delta PS right here. See this? So this is equivalent to partial derivative of your P with respect to S, right? And then delta S divided by 2. And this is an assumption that the particle is small, which is the small particle we're using here. And if you go back to chapter 2, that is our Taylor expansion, just the first term. And you can only do this if it's a small particle. Okay, so you sub that in, continue to solve. You're going to get this partial derivative of P with respect to S, delta N, delta Y, which I showed you earlier is delta V, right, which is your volume, change of volume. So now you basically put this term right up to here, which is why I had this red arrow. And then you have this term right into here. So now you get this side right here. And they already just pulled out the delta V because they're common terms. So now this is your sum of forces in the streamline direction. Okay. And like I said, since it's a recording, it's nice you can rewind if anything was confusing. But to summarize what we just did, we just summed the forces in this direction here. Okay. Now the right-hand side of the equation is going to be this. I say right hand, left hand side, but you could obviously flip-flop them, right? They're equal. So, okay. So we set from the last two slides, we set them equal to each other, right? So this was our MA, this was our sum of forces. And if you put them all together, you essentially get this. I'll explain why I crossed this out here. So what's common between these two terms is this delta V. So that change of volume cancels out. And that basically means in our summation of forces with Newton's second law applied to this particle, the change of volume actually doesn't matter. which is kind of funny because I was wasting my breath doing all the terms for delta V, right? You had the delta N, Y, and S. That was a lot of saying, but yeah, so essentially that cancels out. So right in this side, you're left with delta gamma, which is your specific weight, sine theta minus your partial derivative P times S right here. And then here's the other side here. And the reason why I crossed this out is because in the textbook, they just said this is equal to rho times acceleration in the streamline direction. And unless I missed something or there's something wrong with the textbook, if anyone catches something, let me know, right? I'm open to, feedback, and we're all kind of learning here. But this right here is already acceleration, and rho is right here. So this V doesn't necessarily disappear, which is why I crossed this out, because it should technically be rho V acceleration with subscript S. So I just kept this side of the equation, so hopefully not be confusing. And to get to the equation we're going to anyways, you don't really need this. So, okay, so what we just did, left-hand side equals right-hand side. And this is what we got. So here it is again at the top here. And now we're just making some substitutions, right, with some integration. And this is all in the textbook, and you can review your calculus to do this, but I just made it nice and quick and easy for you. So the sine of theta, we can substitute dz ds. Partial derivative of p respect to s, we can just make that our normal derivatives here, or normal rate of changes. And then here, their velocity times dv ds. If you do your integral, right, you're going to get this. 1/2 dv squared divided by ds. So this is now what we get here, right? So we went from this step here to this step here, applying these substitutions. Okay, so that worked there. This worked out here. And I'm just making sure this worked out here. Okay, yeah. Okay, so that makes sense. So here along a streamline, they just do some more substitution, and what they end up doing here is they move everything to one side to make it equal to 0. So it looks like they added these two terms over here, right? And then this all equals 0. So now we have this, and then it looks like we take out density. Yes, that's what they do. So they take density out of each term, and then I guess you can just put it off to the other side, right? Because it's equal to 0. So you're left with this here. Sorry, I'm getting ahead of myself. That's going to be the next step. Let's okay, so we went from this step to this step here, right? Just putting them all on one side. Sorry, let me take a step back. I'm getting ahead of myself. So this is the equation that we just came from. Okay, this ds from each term is gone now because they're all with respect to s. So now we're left with this term. Okay, and now this is when they take out the density, because you can see in each term there the density somehow, like specific weight is density times g. Density here, if you take out density in this pressure, right, you basically just put the density on the bottom. And here I was reading in the textbook that integrating this pressure term right here is a little difficult because your density is always changing. So you have to assume density and specific weights are constant. Okay, so if you integrate and have the rest of these terms, you have your pressure, right, plus your 1/2 rho v squared plus gamma z. And it's kind of silly. I guess they've multiplied the density back in. So once you do the integral here, this dp, this p just comes in, right, for the integral, and then you have your rho multiplied back in. So I don't even know why they took it out in the first place. So sorry if that's confusing. So now you essentially are left with this, right? When you integrate, you have a constant plus c, which just got moved to the 0 side. So now you're left with pressure plus 1/2 density velocity squared plus your specific weight times the height z equals a constant along the streamline. Okay, so this is basically all our work is up to right here. This is what we wanted, and that's the whole reason why I'm making this lecture. Is once we get onto Monday, we're going to skip the derivations. There's a recording, and this is the equation we're going to start off with in class and do examples. That way I don't have to do examples on my computer here. It's going to look a little bit nicer in class. Okay, so Bernoulli's equation, I listed out, I already said this, typo. I already said this in a few minutes ago, what each variable means. And you'll see this when we do a Bernoulli equation application, right? You can actually set your first location of pressure, velocity, and height equal to your second pressure, velocity, and height. So this is what mainly we're going to use, but this is where it's derived from. And then, right, it's equal to a constant along a streamline. So this is Bernoulli's equation, these two equations that you'll be using for homework, quizzes, and exams. Okay, and here, this is section 4.6.2, confined flows. And this is essentially the idea of mass flow rate from an outlet. So that's the idea of, if you just think of water coming out of your hose, right? Just water coming out of any outlet, right? Or any hole or area. So we use the symbol m dot, kind of like the derivative m dot here. So it's slugs per seconds, pound mass per seconds, or kilograms per seconds. And we also get this term using this as a volume flow rate. So, which is defined by Q, and Q is equal to this m dot divided by density, right? So then your units become exactly what it sounds like volumetric flow rate, which is your volume divided by seconds. And yes, I'm just doing this dimensional analysis in my head just to make sure, right? So if we do, like, for example, kilograms over a second multiplied by the inverse of density, your kilograms will cancel out and volume will be in the numerator. So yeah, this checks out. And Q can also be defined as your velocity times the area of where the fluid's coming from. And here, your mass flow rate, right? If you solve it over here and sub in this QVA, mass flow rate equals rho VA, density, velocity, and area. Okay? And the main reason why you'll need this, and I kind of wanted to explain this now, this is kind of a linking equation for your Bernoulli's equation. So sometimes you're not going to have a variable, and you're going to use these equations to find that what you need to solve Bernoulli's equation. So a lot of times, right, your mass flow rate for one entrance to your inlet and mass flow rate to your outlet, they're going to be equal. And we're going to talk about this more in class. I just wanted to give you a head start on the derivation and I guess what these variables mean. And here, I wrote this in twice because I guess I didn't like this text. So I can delete this. Yes, I wanted to use rho there instead of P. Okay, so we'll go back 2 slides. Okay, so here we have density, right, rho, and then area times velocity, which is your mass flow rate here, right? We just made a substitution. And if these mass flow rates are equal, all of these variables will also be equal from the inlet to outlet, or your 1 and 2. And like I said, I'm just showing this to you now, but we're going to go over examples in class. And you can substitute your... if density is constant, which is a lot of times our assumption is, right, for our problems, these are basically going to cancel out, right? And you're just going to be left with A1 V1 or Q1 equals Q2. Okay? And like I said, the whole purpose of this is these are linking equations. So I know I boxed these in because this is like the big idea, but I would still keep all these equations if you have an equation sheet, because sometimes I'll give density and you're going to have this value to plug in. Okay. We have, let's see how much we're doing on time. 24. That's not too bad. 24 minutes so far. This was in the last slides I posted, right? But quiz is on Monday, January 12th. I will probably do one more announcement. I'm probably making too many announcements, but I don't want you guys to forget and have all the information you need. It's going to be on just chapters 1 and 2, which is essentially your homework 1 that I gave, right? Equation sheets are allowed, only one side of a half sheet of paper. You will not be allowed to write any examples of the homework problems on your sheet. So some people have been sending me other things like, can I put units, or I put like a little note about this variable. Yeah, that's also okay, but just no actual full written out problems, right? And I'm going to look at each equation sheet before we start the test. We already talked about units and constants. You can put that. And right, I'll make another announcement, hopefully no longer than 20 minutes. And this will be done at the end of class, after our lecture. Okay, so it looks like we made pretty good time. And like I said, the time checks out right. I didn't have class Wednesday, so I made 2 lectures to post. And we had class cut short Monday, right, which is why you're watching these videos. So, and that is about it. And I'll probably stop now. And like I said, feel free to always ask me any questions over email. I think I've responded to all the emails already. And just keep an eye out for an announcement from me. So, yep, thank you, and talk to everybody soon. All right, bye-bye.